Hello everybody. So today I will talk about the system design of LeetCode. And this is part 3, and I will talk about these two topics, scalability and near real-time dashboard. Maybe I will focus on scalability only today because it's so late and recently I'm so busy with my job. But let me get started with the scalability. Oh, and the reason why I'd like to go scalability first is before the real-time dashboard is, obviously, we have to know the number of throughput, or maybe, um, yeah, about thinking of this real-time dashboard. So that's why I'd like to do scalability before real-time dashboard implementation. Okay, so I will talk about the scalability. So as usual, I will think of the scalability, this one, from three perspectives. Number one, throughput. Number two, spike of the throughput. And number three, storage size. So let me copy this and put it here, and I will do the back of envelope estimation. So firstly, 300K daily active users. Let's assume each user submit one code in a day. So there should be 300K submissions in a day. So I can say one day is 10 to the 5 seconds. So there are 3K records per sec. So this is a submission. Okay. So 3K records per sec, this number of code has to be executed in the system. And aside from that, we have the search API, search problem API, get problem API. So this can be a slightly larger in terms of the number because this is open to the non-authenticated users. But this is a read request, and submission is the write request, and also it has the spikes, especially in the end of the contest. So I will focus on the scalability of submission. Okay, and also fetch result API. Because let's say we do the polling every 3 seconds, and each question on average takes 10 seconds to be executed, and the submission is, result is ready. In that case, this fetch result API throughput is 3K times 3, which is around 10K records per sec. So this is not so big number actually, but yeah. And fetch ranking, I will talk about this later when I talk about the real-time dashboard. So these are two numbers I will consider. I didn't do the back of envelope estimation for this search problem and get problem API, but because what we're doing here is the throwing the query to the PostgreSQL. So what I can do is, if the number read request is so, overloading the server, we can put the read replicas. And also, problem service, this is a stateless. The request is stateless, so this can be scaled out horizontally. Let's say like AWS auto scaling by the kind of CPU usage or memory usage threshold. So that's what I can do about this layer. And API gateway, this is it's a cluster of servers. So this is internally as the mechanism scales out. So it's totally fine. Okay, so now I'll talk about the submission. So there are 3K requests per sec. So this is not a big number. Um, so for API gateway, as I said, it scales out. Submission service, yes, this can be scaled out because um, you know, yeah, each submission request is state breath. For Kafka, 3K requests per sec, this is totally fine. So it's totally fine. Yeah, you can push it. And creating the recode in database 3K requests per sec, this is totally fine because, let's say PostgreSQL, it can handle around 10K write requests per sec, so 3K is totally fine. Yeah. So now the problem is this execution worker. If I use only one topic in Kafka, which means that there is only one consumer worker which subscribes from that topic, which means that this single server has to execute the code. I mean, 3,000 code every sec. This is completely not feasible. So what I will do is I do the partitioning here. And I can use the partition key to be the submission ID. So the thing is, in Kafka, the messages in the same partition is executed in the first in first order. But for the other topics, I mean, across the partitions, the order of the execution is not guaranteed. So that being said, I use a submission ID as the partition key. Yeah. So in this way, the programs are submitted into partitions evenly, and yeah, execution worker, which is equal to the number of number of partitions, in parallel executes the code. Of course, each worker can boot up multiple containers and work on it. That's totally fine. Yeah. And yes, this update is only once every question. So this is 3K requests per sec. And this creation is also 3K per sec. So in total, it's still 6K. Yeah. And for this submission result service, this reads the data from submission DB. But this is 10K requests per sec. I will write it down. This is 3K requests per sec. Similarly, this is 3K requests per sec. This is 10K requests per sec. Yeah. So what I can use here is, again, I can use the read replicas. Yeah. The log is around 2 or 3 seconds. So I think it's totally acceptable. Yeah. Okay, so yep, this is what I will do here. Okay, but if we really wanna make it, synchronous. I mean, okay, so what I mean to say is the data synchronization from the master node to read replicas takes a few seconds typically. And if this time lag is not acceptable, what I will do is do the sharding. So sharding by maybe user ID, because it's typically the submission for the same user is fetched in bulk in many cases. So I will do the sharding with user ID. And when I think of doing the sharding, maybe I will use the DynamoDB, because in DynamoDB, as long as I specify the partition key correctly, DynamoDB internally does the sharding with consistent hashing. So that, yeah, something I would consider in the production system. But anyway, yeah, that's something that's how I can handle the queries. Okay. Okay, so now we talk about the second perspective, spikes. So in the end of the contest, let's say the request becomes 10 times. So submission service creates a record 10 times, pushes the message into Kafka 10 times. Submission result service fetches the result 10 times more. With, yeah. So this becomes 30K, 30K, 100K. So in this case, as I said, this submission DB PostgreSQL cannot handle all of them. So as I said, I can think of doing the sharding of the database. For other components, they are completely scaled out. They can be scaled out. For Kafka, before the, during the contest, I can kind of increase the number of partitions. Yeah. And I can increase the number of execution workers. So that's totally fine. Yeah. So that's something I can do. Okay. Yeah. So as the alternative approach, I can think of using AWS Lambda here. So Lambda is the computation service provided by AWS. And if I use that, I would go with SQS, because they are very, easy to be used together, because both of them are provided by AWS. So with that, I can specify the, runtime of the Lambda. So I can easily choose which of, languages, Python, Java, Scala. Yeah, I can, I don't have to build the container one by one. All we have to do is specify AWS Lambdas that we want this number of Lambda servers working with Java runtime. So yeah, that's something we can do. And that being said, yeah, if I used AWS Lambda, there is one problem. It is possible that I do the auto scaling according to the number of messages in the SQS, but there is a problem named cold start problem. The cold start problem is when there is a spike in the traffic, in this case submissions, AWS Lambda scales out, but it takes some time until it catches up. So considering that, I can warm up the servers, which means that we specify that around the end of the contest, or maybe during the contest, we boot up the number of parameters with much buffer. Yeah. So with some buffer of the Lambda servers, even if there is a spike in the end, we have enough number of computation ready already, so it can handle the spikes. Yeah. Okay, that's it. Okay, so now we talk about the storage size. Actually, I don't have a big concern on this system about the storage size. Firstly, for programs, I can say there are up to 4,000 programs in LeetCode, and it wouldn't go beyond 10K. Or I should say, every year there is 50 contests, maybe including weekly and bi-weekly, maybe 100 contests, and in each there are 4 programs. submitted. So I can say there are 500 questions added in a year. And let's say each have 1 kilobyte size. No, maybe 10 kilobyte because there are many test cases. So assuming that, I can say this is 50 megabyte. Very small. Yeah. So I can say in 100 years it becomes 5 gigabytes. So storage size wise, this is completely easy. Yeah. Submission is a kind of concern, rather, because there are 3K requests, 300K submission per day. And let's say each has 100 bytes. No, maybe 1 kilobyte. It includes the solutions and also the test case results. So in total, in a day, this becomes 300 megabytes, right? Oh, this is quite much. So in a year, this becomes 1000 gigabyte, 100 gigabyte. But nowadays, AWS, for example, Aurora can store 100 terabytes of data. 552 terabytes of data in the storage. So how many days? So yeah. Okay. So this takes 5,000 years to, yeah. I mean, run up. Sorry, run as a storage. So again, this is totally fine. Yeah. Okay. So storage size wise, there is no problem here. But maybe what we can do is the submissions. The old submissions are not referenced so often. So maybe I can move some old data, like more than 3 years, to the cold storage, like S3. So in this way, we can, we can save the cost of the database because obviously S3 is much cheaper in terms of the cost. Yeah. Okay, and of course, because as I said, the access pattern is typically, per user fetching. So maybe we can store the submissions from the same user or maybe same question for same user in the same file. But yeah, never mind. There shouldn't be so many, data for one user. Yeah. So maybe what I can do is for one user for 1 month would go into the same S3 file, S3 object. In that way, when user scrolls down and fetches the old question submissions, maybe it has some benefits that we don't have to get in fetch and return. Sorry, because cold storage takes time to fetch the data. So with that accumulation, maybe in some cases we can save some time until the data is returned to the user. Okay. Good. So I talked about the scalability here. So now I will talk about the near real-time dashboard. So for the near real-time dashboard, in each contest, okay, so in each contest there are 10K participants, and actually, okay, So let's say each user makes 5 submissions, or I should say, on average, 3 questions are solved. Maybe 2 questions. Per user. So I will assume this number. And also I will assume there are 10K, because 10K users are viewing the dashboard. So typically, this dashboard is open while the contest. So I can imagine that maybe many users open the dashboard while in the another screen, another display, while they're in the contest. But after the contest, there are real users who open the dashboard probably. So I will think about the, obviously dashboard throughput while the contest, during the contest. Okay, so the thing is, there are 10K users opening the dashboard, and for each, as I specified here, this is refreshed every 5 sec. So there are 2K requests per sec to refresh the data. Yeah. So firstly, I can say if this query, very complicated query, is, executed 2K requests per sec, the database is heavy loaded, overloaded. So I have to think of another way aside from this complex query. So that being said, the most kind of straightforward idea is pre-compute the data, or I should say cache the data. So let's say we cache the data in the Redis. So there is a user who opens the dashboard, and then that first user, throws a query and it gets the whole ranking for 10K users. Then it stores it in the Redis, and then it is returned to the user. And this Redis basically doesn't have TTL, but another user, after 5 seconds, that user doesn't fetch the data from Redis, but throws a query and get 10K users ranking and stores in the Redis, and then returns the response. So in this way, every 5 seconds, there is a user who is the buttrock and has to wait for the query to be executed. So that's the first approach. And I will quickly say how to decide which user's request should go to database to get the new ranking. So I can kind of use the kind of rock. So here I quickly include the rock here. So every 5 sec, okay, let's say, so we create the rock here, and if this is rocked, user doesn't have to, user doesn't have to make the request. So from this contest ranking service, it quickly checks if the rock is true or false, and if false, atomically it takes the rock with TTL 5 sec, then makes a query and gets the rated ranking and put it in the Redis, and that's it. And after 5 sec, this rock record is deleted, so another user, can acquire the rock, and the same thing happens. So this works because Redis is basically single-threaded. So that's the first approach. But I don't want that bad rock user to wait for a long time. So instead of that, what I can do is I can put a kind of server worker, cron job server. So this makes a query. So this is run every 5 sec. Then it writes, or I should say, overwrite the latest ranking onto the Redis. Then with that, this query is here. So this is not needed. So there isn't a bad rock user who has to wait for the query to be executed for a long time. So that's my second idea. Okay, so I'd like to be more specific about this Redis here, just in case. So I use a Redis sorted set. So key is let's say contest ID, and I use a sorted set here. So I can say this should be the kind of topper of number of solved questions problems, AC accepted, and last timestamp as a tiebreaker, and then user ID. So I will store this in the context in the sorted set. So the good thing is when user opens the dashboard, we need, of course, the pagination. So user would like to get the ranking, let's say in the third page, it should be 200 first to 300, maybe, for example. In that case, it can fetch the exact record with log 10k plus 100 linear scan. Yeah, so I use the sorted set here. And I'd like to make a quick update on this. So this is a good idea, I think, to use the cron job and update the Redis. But the thing is, we don't have to throw this heavy query to the database even 5 seconds. So this kind of query is, can cause some problem on the database. So instead of that, what I can do is use the change data capture. So, okay. Here, I use the change data capture, and this instead of the worker. So I would call it ranking update worker. So the good thing is when the problem is submitted, submission is submitted and the result is updated, that change data capture, with that change data capture, this ranking update worker can know if the submission was accepted and if that problem is for that contest going on. So if both of them are submitted, it can change the rank of the user. So if both of them are true, this ranking update worker fetches the current users all the submissions. in the contest, fetch ACs in the contest. So now let's say there are two problems already solved by that user, and if this is new, if the user could solve the question as the third. Okay, sorry. So I can just say if this worker finds a record which is inside of that contest and AC accepted, then this ranking update worker just makes a query to submission DB to get the number was accepted and last timestamp with this query. So this query is quite small. Yeah, I mean, this query doesn't override the database because this is quite simple query. And now it updates the Redis, the record in the Redis with new, number acceptance, last timestamp, user ID, tuple. So that's something I can do here. Yeah. And now this Redis, ranking data is up to date. So now user, of course, this is the Redis. User can see the dashboard really quickly, thanks to the sorted set. Okay, so this is it. Oh, maybe I have to mention that when updating the record in here, it cannot, it has to linear scan all the data in the Redis because data is sorted by number of AC, Rust TS, user ID. So, maybe it is possible, yeah. So maybe this ranking update worker has two records. So number one, current number accepted Rust timestamp of that user ID, so it can access that data quickly and delete it, and also insert the new data with the new number accepted and Rust TS user ID. So in that way, and both of them should be done atomically. So in that way, it takes only login time to delete and insert the data into Redis. Okay, so this is it. So today I talked about the scalability and also new real-time dashboard feature design. So that being said, I finished my today's system design practice. Thank you so much. Bye.